Hello, I'm back. This will be a review for Unit 2 of Chemistry in the Spring. Although it says Test 3, remember the first test was just the elements test. So this is really the second unit of test. And when I looked at this, it doesn't seem like a lot. So I'm not sure if it was difficult for you guys or easy, but in retrospect, I hope it's going to be easy. Let's go over the things to know for the sheet. I'll try to do this a little more quickly than I did for the last review. Although in this review, there are some sample problems that I'll go ahead and do, so maybe it will take just as long. But when we get to the problems down here, there's a lot of repeats, and maybe you found that useful, that I asked the same type of questions over and over again, because I think you did get good at them. Okay, so let's get started. No, you do not need to memorize the polyatomics, and I'll show you why. I forgot to put this on the on that document there, but I'm going to give you this sheet. So notice that we have the polyatomics listed. They're the negative ones right there, the 5 negative ones. But the positive one is right there. Okay, so if you're looking for ammonium, it is on that sheet. Okay, so we're going to come back to that. We'll use this little chart a little bit later. But let's get back to the review sheet. So yeah, you don't need to memorize it, but if you want to write them down on your cheat sheet, go ahead. History of the atom, not a lot. So it's hard to kind of be specific, but I'm not going to ask you a lot of stuff about Dalton or Thomson. I think I still want you to know the classic gold foil experiment of Rutherford that found the nucleus or had evidence for the nucleus, and a little bit about this stuff here, which I guess is history, about Planck and quantum theory and Einstein and photoelectric effect. Not much, and it's still less likely that I'll put something from those topics than I would put something, but just to be safe, I'll go over it a little bit. Some of this right here, the EM spectrum, we learned in a previous unit, the wave unit actually of physics. Still know them, so I'm not going to reteach it, but make sure you have written down your Roy G. Biv and RMI VUXG and know what order that is. The new thing in this unit is, I think I kind of have it out of order, well, not really out of order, but I taught it a little bit later, is we found out that Einstein came up with this formula for the energy of a photon, which is proportional to its frequency. So previously in the physics unit, we just ordered them according to wavelength and frequency, but now we can also order them in terms of energy. But the couple of new things here, well, I guess really the main new thing here is thermal radiation. And again, I don't know if I have enough space to add a question about this. It's nothing that we did for very long, so it's unlikely I'm going to ask something about that. But that's the whole idea, which I'll explain again a little bit later when we get to the problems, that everything is emitting its own radiation. Sure, I reflect radiation. I'm wearing a blue shirt. I'm reflecting blue light. But my body is giving off radiation as well. It's just that room temperature objects like your body or the table or a building is giving off infrared that we can't see. And the hotter the object becomes, the higher the frequency of light that it emits. So if you get an object hot enough, it might just start to glow kind of a dull red, like you put a piece of metal in a fire. Then it might get yellow hot or white hot, and then maybe even blue hot. And theoretically, if it's hot enough and it didn't just completely vaporize into a gas, maybe ultraviolet hot. So that's that idea that I'll mention a little bit later, but it's unlikely I'm going to ask a question about that. If you know it, the pattern, then it might not be something you need to write down. But if you have space, you might as well write it down. The quantum theory, as I'll see I'll point out a couple of questions, as you'll see later, is just basic ideas. Know that Max Planck was the guy who introduced it. And the main idea, which I have highlighted here somewhere, the basic idea there are different ways of kind of defining what quantum theory is. But the main thing that I would say is that unlike classical theory, which says any property can take on a continuum of values, any possible value whatsoever, and all values in between infinitely, the idea of quantum theory is that properties can only take on stepwise values, incremental values. They can't have the in-between values. That maybe is not so relevant to our lives, But in the quantum world, in the physics world, in the very small, it is incredibly relevant. And we'll get to that in terms of the atom. And then maybe for the photoelectric effect associated with Einstein, who explained it and for which he won his Nobel Prize, kind of maybe understanding what the photoelectric effect is, what was the problem, and how he solved it. So again, when I get to the problem later, we'll talk about that. And then this is our new equation for light. We didn't have many equations for chemistry. E equals hf. The energy of a photon is the Planck's constant, which would be given to you, times the frequency of that type of light. But we can combine it with the equation we learned in the last unit of physics, that the speed of light, c, is equal to the wavelength times the frequency. And when we do so, we could get these two equations. So one way that we solve them, as you'll see when we did the homework, is we use one, then we use the other. But I said, even though I wouldn't give you those two down here, you can memorize them and do it in one step. Like, in other words, go from energy to wavelength, or go from wavelength to energy. Go ahead and write those down on your test, on your cheat sheet, because I will probably give you a question where you're going from either energy, E, to wavelength, lambda, or lambda, the wavelength, to E, energy. So you could do it in two steps again, first using E equals hf, and then using C equals lambda f, or vice versa. But you could just do it in one step. Again, I would give you H and C. So again, I'm just going through these quickly until we get to some, I don't think we've hit any yet that are particular problems, have we? No, not really. So then we started learning about kind of building on the history a little bit about spectra. So no, as we'll see when I go over the problems, I'm not going to try to explain them too much here. The three types of spectra that we talked about. One is the continuous spectrum, which is what dense objects like solids or liquids give off if they're heated to a high enough temperature that they can give off visible light. And it would give off every single wavelength of visible light roughly equally. So it would look kind of white hot, let's say. So there's no gaps. There are no gaps in the spectrum. Then you have the emission spectrum, which visually would just be kind of blank, except you have an occasional colored line. So just these discrete colored lines. And as I'll explain a little bit later, you get that when you take some low density gas and you heat it up, you energize it, you run a current through it. When you do that, it produces the emission spectrum. And then the absorption spectrum, which is almost looks like a continuous spectrum, the full gamut of colors, except that occasionally there's a discrete dark line. And you get that by taking like a continuous spectrum, like a white light source, like a light bulb, and you run it through a intervening low density gas that's cool. And that gas seems to absorb certain colors of light, which is the cause of those dark lines. Again, once I get to those problems, you'll see what I mean. What else? I won't ask you this, but this is the idea where quantum theory comes into atoms, is that Bohr used the quantum theory to explain why the spectra exist. And so he postulated that, well, basically, I'll say it this way, electrons can't have any energies around the nucleus. They could only have certain particular orbits and not in between orbits. They could only have the energies of this orbit, or that orbit, but not the orbits in between. And in doing so, he was able to explain the spectra. As far as terminology, it might come up. I'm not going to ask you a question specifically about this. I could for one of these. I have on the homework and on the quizzes. The lowest energy state is called the ground state, and all the ones above it of higher energy are called excited states. And this is the one that I catch people on usually. We also give them like little letters. So the ground state, I'll just write it here, is n equals 1. That's the ground state. I'll just put GS. Then you have the next orbit is n equals 2, then n equals 3, and so on. Those are the excited states, the ones that are not the ground states. Okay, this is not writing very well. I'm using a third-party pencil. Skipping. But anyways, the n equals 2 state, that is the first excited state. So the first excited state is actually n equals 2 because the ground state is n equals 1. And then n equals 3 is the second excited state. That said, again, I don't have a lot of questions I can kind of waste on little simple questions like that, but it might come up, who knows. All right, let's keep going. I'll get my highlighter. And again, we'll do some problems. So if it seems like this is going quickly, I'll slow down a bit when we get to the problems. Know that when an electron or when an atom or electron absorbs a photon, when it absorbs a photon, the electron gets promoted to a higher energy excited state. So it's going up the ladder, so to speak. And the photon that it absorbs, well, I guess I'll just stick with that bullet for now. But when the electron falls back down to a lower energy state, it's emitting a photon. So absorption spectra involves electrons going up to higher excited states, and emission spectra involve electrons falling back down to lower excited states or to the ground states. But then specifically, this is the key idea that was kind of used by Bohr to explain the atom, is that the energy of the photon that is going to be absorbed or the energy of the photon that is emitted must correspond exactly to the energy difference between two orbits. And if it doesn't correspond exactly, that electron is not going to be moving up or moving down, or is not producing a photon of that energy. I kind of butchered that, but it's hard to kind of describe it if I'm talking both about emission and absorption. Again, we'll see that once we do the problems. It's actually kind of an easy idea. And then related to what I said before, we can incorporate using those equations in a Bohr atom problem. And you'll see what I mean. I put a lot of Bohr atom problems on there, and we'll do probably a couple of them. Now, here's some good news for you. I won't have you bother memorizing the colors of flames. I should, we just didn't practice it much. And I did for the test, so let's not do it for the final. Okay, what's next? Then we started talking about elements versus compounds. A simple idea is an element is just made up of one single element. So for example, helium, O2, S8, those are all elements because there's only one element that makes each one of those. Compounds, very simply, are made up of two or more different elements like those. That's not so important. But what we started talking about, well, let me cover this first. I probably won't ask you a question about this next bullet, but I could. That just the idea that the properties of a compound are going to be totally different. Well, I guess most are going to be totally different than the properties of the elements that make up that compound. So you're looking at NaCl, for example. NaCl salt has totally different properties than sodium or chlorine have. Again, probably not going to ask a question about that. But here's kind of a key point of this section. I probably overkill. There are probably like 20 questions I've asked involving this, is that there are two types of compounds, molecular and, where did I write it, ionic. So molecular compounds are made up of non-metal atoms only. So those on the right side of the periodic table and hydrogen. Ionic compounds are made up of a metal plus a non-metal, but more generally, I'll say a positive ion, cation, and an anion, because it could involve a polyatomic ion, which I haven't mentioned yet on this video. So anything that involves ions is an ionic compound. So here we go. Here's our first question here. Which of these is an ionic compound and which is a molecular compound? Well, Cu and F2, that's a metal and a non-metal. Copper is a metal. Fluorine is the, essential, not essential, but the definitive non-metal. And so that's ionic. But CH4 involves two nonmetals, so that is molecular. And then, I guess that's the only question there. Ionic compounds are held together by ionic bonds, and molecules are held together by covalent bonds. I brought that up, but it wasn't a big deal in that unit. It wasn't until the final unit that we started talking about molecules and covalent bonds. But just understand that if it's going to be an ionic compound, what holds it together is what we call ionic bonds. And if it's a molecular compound, what holds it together is what we call covalent bonds. Okay, then another hopefully simple idea is coming up with the chemical formulas. Now, I introduced just generically a chemical formula, including molecular formulas for like molecules, for example, CH4 or C3H8 over here. But we focused for this unit just on ionic compounds and the formulas of ionic compounds. And one of the key ideas is we just give what's called an empirical formula for ionic compounds, the lowest whole number ratio for that compound. There is no need to have unnecessarily high subscripts because it is just one big repeating pattern anyways. So why write Na100Cl100, we're just going to write the ratio of one ion to the other, NaCl. So that's an empirical formula. Just a reminder, nothing new for this unit, but because it's an idea we're using to come up with chemical formulas. Understand that if I mention cations, I'm talking about the positive ion. If I'm mentioning an anion, I'm talking about the negative ion. Sorry, my throat's kind of sore, so I'm talking kind of weird. Again, another reminder, and there are lots of questions about these two, that topic as well, even though that's from last unit. We're going to need to know that knowledge, which is why I implanted that idea as early as possible. But here's one of the key questions, not the biggest one, but coming up with the empirical formula of an ionic compound made between a metal and a nonmetal, or between a cation and anion, because that could be inclusive of polyatomic ions. So let's go ahead and do this. What will be the empirical formula of the ionic compound formed between lithium and oxygen? Just as a reminder, I hope you haven't lost this skill. Maybe I'll zoom in so we can see that. Lithium is going to form what ion? Well, I don't have a periodic table here, but gosh, I hope you remember this. Not that you need to, I'm going to give you a periodic table, but I'm hoping after all this time, you remember lithium is an alkali metal, which has a +1 charge. And I hope after all these examples, you remember that oxygen is -2, or 2-. So the whole idea of getting an empirical formula for an ionic compound is that you want the charge to be balanced. We need to have more, sometimes have more of one ion than the other to get a neutral compound. So hopefully I don't need to explain this to you. I'm going to need 2 lithiums for every oxygen. So that formula is going to be Li2O. Remember that the number refers to the element in front of it. And that would give me +2 to balance out the -2 of oxygen. What about aluminum and sulfur? Aluminum is 3+. Sulfur right under oxygen is going to do 2-. So how do we balance the charge? By having Al2S3. There's that little trick I told you about, that whole switcheroo trick. It pretty much works. So if one's 3 and one's 2, just switch them for their subscripts, except pay attention that you might need to reduce the subscripts once I wrote it together. If we get to a problem like that, I'll point it out. But don't do it if you're confused by what I mean. Just do it the way that kind of makes sense to me is just we're trying to get the charge to balance. So I'm looking for that lowest common multiple, if that's the term from math. So here's something you don't need, is I mentioned this earlier. It said for the test, you need to memorize those 6 polyatomic ions by heart. It's on the solubility table. Do not forget to look on the solubility table that I give you. They're all listed there. Know how to find chemical formula for ionic compounds involving polyatomic ions. When to use parentheses, when not to. And then later we're going to see when we use Roman numerals. I'm doing this as a separate bullet here because we learned them in small little waves. So the whole idea when they have polyatomic ions, nothing new, except sometimes we might need to use parentheses before we put the subscript so we don't get numbers confused. And it's kind of obvious when you do these. So let's just do the examples here. What's the empirical formula for the ionic compound formed between ammonium and carbonate? So if you didn't know, look at the solubility table, and you'll find out that ammonium is NH4+, and you'll find out that carbonate is CO3 2-. I hope you still remember those. So the whole idea is getting them balanced, right? So we're going to need 2 ammonium ions to balance the carbonate's -2 charge. But I can't write NH4, and if I need 2 of those, 2 CO3, that looks like NH42. So the idea is you enclose the polyatomic ion in parentheses, and you put the 2 outside of it. So if you can't see that, I wrote NH4, parentheses, 2 CO3. What about calcium and phosphate? I'm running out of room. Calcium is an alkaline earth metal. Again, I hope you've remembered that. And phosphate, again, this pen is not the greatest. Phosphate is PO4 3-. So another one of those 2-3 tricks, the switcheroo trick. So it's going to be Ca3 PO4 2, because 2 PO4s give me -6, 3 CAs give me +6, so it balances. And again, I need parentheses so it doesn't look like PO42. Okay, now the last round that we did to name things is we named ionic compounds where the cation is a metal that is not one of those metals that always forms the same charge. It's, for example, a transition metal, although some metals that aren't transition metals also do this. They can form different charges, like lead, for example. Lead's not a transition element, but it can form different charges. So if it's a metal that could form different positive charges, we indicate the charge with the Roman numerals. So what does copper 2 mean? It means the copper 2 plus ion. It doesn't mean we have 2 copper ions. It's telling us what the charge is, okay? So keep that in mind, and as we do problems, I'll point that out, so I'm not going to spend a lot of time repeating that. So one skill you'll need when we name compounds from their formulas is to figure out the charge of the ion, the metal ion in that compound. So what is the charge of each iron? Not iron 2, the iron subscript 2, but what's the charge of each iron ion in the ionic compound Fe2O3? Well, what is the charge of each oxygen? Each oxygen is -2, right? So the 3 oxygens give us -6. I'm slowing down a little bit because I think this is the first time that might get a little confusing. So if the 3 oxygens give us -6, the 2 irons better give us +6. So what must be the charge of each iron ion? It must be +3. I hope that made sense. And I didn't mean to go so fast for like these. I think it's something that we've been practicing quite a bit, but I'll do more problems below. Don't worry. I'm going to go over a lot of the homework problems. Penultimate bullet, know how to find the chemical formula for an ionic compound involving those metals with varying charges. So if I said, what is the empirical formula of the ionic compound formed between lead-4 and sulfate? I had to tell you lead-4 because lead is one of those that could form different charges, usually +3 or +4. So I couldn't just say formed between lead and sulfate because you wouldn't know which version of lead that is. So remember, lead-4 means we're talking about Pb4+, not that we have 4 lead ions. And sulfate is SO4 2-. So I'll do that even odd trick again. I'll tell you why you have to beware. If you did the even odd trick, you'd go, let's switch the 2 and the 4. So I would write Pb2 SO4 4. We did the switcheroo. Not the even odd trick. I said that wrong. That's my other trick for balancing equations. The switcheroo trick here is you just switch the ion charges and put them as subscripts, but reverse them. So you see what I did? But it's an ionic compound. So should I write Pb2 SO4 4? No. Why make the numbers unnecessarily big? So you would miss that problem on a multiple choice. We should write it as Pb SO4 2. So again, the easier way, I get, well, if it's easier, but just the more logical way is, what combination of those 2 ions do I need for the charge to balance? Well, I need twice as many sulfates as I need of leads. So I'm not sure if that switcheroo trick is actually worth it. And then I'll deal with the last, my throat is really hurting, sorry. I'll deal with that last bullet when we get to the problems. It wouldn't make too much sense just trying to talk about it now. I'm going to try to talk a little quieter so my throat doesn't hurt so much. Hope I'm not getting sick. All right, so then we get to naming. That was more about formulas and coming up with formulas. But we want to get to naming. Sorry, this way that I'm recording, there's unfortunately no pause feature. I can record multiple videos, but then it becomes a problem of stitching them together, which is a little time consuming. All right. So now to name these, I'll go ahead and do a little mini lesson here. And then when we get to the problems, I hopefully won't have to do the mini lesson again. So instead of writing them, let's just refer to what's written here. I hope you can see that because I can't zoom in so much more that you can't see all the whole text. So it's for ionic compounds. This unit wasn't about molecular compounds, just ionic compounds. So we're looking for something made up of a cation and anion. To make it sound simple at first, all you're doing is naming the cation, which is always first in the formula. Don't get tricked. And then you name the anion, the second thing in the formula. That's it. Okay, you just name the 2 things. But of course, there are a couple of special rules. If the cation is an alkaline metal, alkaline earth metal, or group 13 thing like boron or aluminum or gallium, you do not use Roman numerals because we always know their charge. And that's what we got used to first, and so people kept forgetting to put Roman numerals when they needed to. But if it's any other cation besides group 1, group 2, or group 13, you need to indicate the charge of that metal ion with Roman numerals. Now again, truth be told, by convention, there are some transition elements where we don't include it in Roman numerals because they actually do always form the same charge. But for this class, I don't want to get hung up in a bunch of exceptions to rules. You can worry about that later. Now, the second special rule is we always end the second element in "-ide" if it's a monatomic ion. Doesn't mean it has to be one single atom of that ion. It's not one of our polyatomic ions. But if it's a polyatomic ion, we don't change the ending. Okay, so we'll get plenty of examples. You'll probably want to skip once we get to the homework to say, okay, enough of these. So magnesium, we have MgCl2. We just name the two things. So we say magnesium. Now, do we need to say magnesium 2? No, because although you might not have a periodic table in front of you, it's an alkaline earth metal that's always +2. So why insult the listener by saying magnesium 2? It's like, well, duh, I know it's 2. So we don't write Roman numeral 2, it's always 2. And then it's chlorine, but we always change the ending to chloride if it's a monatomic ion. So magnesium chloride. CO3PO42, we say calcium, and again, it's an alkaline earth metal. So we don't write 2, it's always 2, but we call it calcium phosphate, not phosphide, because it's a polyatomic ion, and you don't change the ending of the name of a polyatomic ion. If you did and called that phosphide, that's not phosphide. Phosphide is the P3 minus ion. It's the ion of phosphorus. So don't change it to phosphide. And then how about manganese or MnCO3? Well, that's a tricky one. What's the charge of manganese in this compound? It's one of these elements, a transition element, that can form different positive charges. Well, if each carbonate is -2, right? And we have 3 of those carbonates, that's -6 altogether. And there's only one manganese to balance that whole -6, so it must be +6. So what we write is manganese, not magnesium, 6 Vi carbonate. And we don't change it to carbonide or something, or carbide, because carbide would be the negative ion of carbon. Same thing with sulfate versus sulfide. Know that SO4 is sulfate. Sulfide is S2 minus. Okay, now going backwards is if I give you the name, you should be able to come up with the formula. Oh, let me just stop for a second. At this point, I didn't introduce naming of molecular compounds when we were learning this. Later, we learned when we did molecular, we would do things like adding prefixes like di or tri or tetra. We do not use those for ionic compounds. Do not use those prefixes for ionic compounds. We use them only for molecular. Okay, so the next review, I'll go over those. So what's the empirical formula for sodium sulfide? The way you do this is you say, well, sodium is what charge? It's an alkali metal, so it's +1. Sulfide is not sulfate. It's the S2 minus ion. So it becomes just like the problems up here, where we're just saying, what will be the chemical formula between Na plus and S2 minus? Well, it's going to be Na2S, right? So really, it's just the same problem we were doing earlier, but just phrased in a different way. Okay, how about aluminum hydroxide? Aluminum is group 13, it's always +3, and hydroxide is the OH minus ion. So what's going to be the formula? Well, we need 3 hydroxides, so AlOH3. Vanadium, that's not, well, it's a V, but that stands for the Roman numeral 5. Again, this pen isn't great. So it's saying that I have the vanadium 5+ ion, and sulfate, not sulfide this time, is 2-. And this time the old switcheroo trick works, or you could just think the lowest common multiple is 10, so I need 2 vanadiums and 5 sulfates. So we'd write it to V2, SO4, 5. Usually I try to use examples that actually do exist. I think that one exists, but I'm not positive. So then we're kind of getting close to done, so hang on, and then we'll start doing some problems. Solubility and precipitation. Now, a lot of what I did, you'll see, are a lot of drawing stuff. And I know it might have been kind of annoying when you did that. But the reason why is I really wanted you to understand the process of dissolving. And I'm not going to ask you, of course, to do that on a test. You're not going to be drawing beakers with things falling apart. So this will actually go quicker when we go over the homework in a moment, because I won't be asking you so many drawing things. We're just going to get to it. Now, I'm not going to, well, maybe I will, maybe I won't. I don't think I will, but I could. Know these definitions, so know what the it might be a nice question to ask, so maybe now I think about it. I don't know if I will, but I might. Soluble, solvent, solute, aqueous, saturated, all those things. So if something can dissolve, we say it's soluble. We call usually the liquid. When we're doing chemistry, we usually dissolve solids in water or liquid. The thing you're dissolving, which is usually the solid, is the solute. And the liquid that you're dissolving it into is the solvent. And then you make what's called a solution. And if the solvent is water, we say it's an aqueous solution. And saturated just means you've dumped as much or you've dissolved as much solute as you can. And the solvent cannot hold any more solute in it. It's full of solute and you can't dissolve anymore. Again, sorry, I'm not the most eloquent today. I'm kind of butchering things, but I'm just trying to get through this really quickly so we can start doing problems. I just mentioned that. So aqueous solution is just something that is dissolved in water. What does that third bullet say? Yeah, we won't draw, so don't worry. But there could be something where I draw, and I'll show you problems like this. You might want to interpret the drawing, but you can't draw. But I might have a drawing and have you say something about it. Fourth bullet, know how to provide. Yeah, so it's solubility table to see if something's soluble or not in water. Understand what precipitation is. We'll get to a question or two like that. Using the solubility table to predict whether a precipitate will form. Write the empirical formula of precipitate. So these are things I'll go over when I do the problems. Spectator ions, the typical double replacement reaction is a precipitation reaction where we mix two aqueous solutions, and usually, if a precipitate forms, a positive ion of one solution will get together with the negative ion of the other solution and form a precipitate, a solid that falls to the bottom of the beaker. And the other two ions don't precipitate. They're just still floating around in the solution. We call those spectator ions because they're not part of the action. They're just spectators. The action involved the two ions that got together to form a precipitate. And you won't draw. Okay, then this, I think the word's vacillating between whether I'm going to include this or not. I'm leaning towards no. I'll go over it, try to learn it, try to write down this, but we didn't practice this enough, partly because I was going to practice it some more when I was going to do a day or two of acids and bases, because pH involves molarity. And so earlier on, I introduced molarity in kind of an anticipation that we'd be using molarity. Plus, we did labs where I talked about, 2 molar solutions. So I want you to be aware of it. Molarity, unlikely it'll be on it, but I'll still go over it. But one thing you do need to know about is, again, molar mass, which I went over before, and how to convert between grams and moles using molar mass. So let's go ahead and do that sample problem that was there. I think I didn't have any other sample problems that I skipped. So what is the molar mass of C3H8O? I started doing these problems where I kind of felt guilty not guilty, but disappointed is the better word, that people have such a hard time with finding the molar mass of simple molecules like this, because you should know the masses of like 10 different elements that are so common in compounds. So anyways, I don't need to use a periodic table because I have that super skill. Carbon is 12, hydrogen is 1, oxygen is 16. So what you do to find the molar mass is you add them all up, taking into account how many atoms of each there are. So I have 3 carbons, so that's 36. I have 8 hydrogens, that's 8. And I have 1 oxygen, which is 16. So that's 60. So the molar mass is 60 grams per mole. Okay. But then this is a skill we did in the last units, converting between grams and moles, mass and number. But then I just did elements. Here now we're doing compounds. So remember what we do is we start with what's given to us and write this down on your cheat sheet, a sample question so you know how to do this. What we use for the conversion factor to go between moles and mass is the molar mass. So on one side of that conversion factor, I'm going to write 1 mole, always 1 mole on one side. And the other side, I'm going to write 60 grams. What am I going to put on the bottom there? 1 mole, because we want the moles to cancel. Remember, that's like 2.5 over 1. And I'm going to put the 60 grams on the top. So we end up multiplying, and you get, it's 150, right? I assume so. 150 grams. How many moles is 200 grams of that? Well, we start with what's given to us, and then we use again the molar mass, but this time I'm putting the 60 grams on the bottom because we want the grams to cancel. And so you do 200 over 60, which is 3 1/3. And we're solving for moles. So know how to do that. I am going to ask just one question on converting grams to moles. If you miss it, you weren't paying attention to this. You should be able to write this down on your cheat sheet and just follow the pattern of what you do to either go from moles to grams or grams to moles. And then again, you know what? Let's not do it. I just made up my mind. Okay. I feel guilty because we didn't practice it very much. And so, yes, I could spend some time saying, hey, let's relearn this and do it. I wish I spent more time on it because I'm sorry that I didn't kind of follow through with that. But let's just skip it for the final. We did it on the test, so no big deal. And then the last thing, this was kind of getting us ready for getting into molecular compounds, which was the next unit. But things we already did at the beginning of this unit, know how to differentiate between a ionic compound and molecular compound based on its formula, which again, we're going to see a lot of problems like that. The idea that we always reduce an ionic compound to its empirical formula, yes, I'm talking super fast. And then that's the key point, is I don't know if it's going to be on the final because I don't know how this would lend itself to a question, but understand that ionic compounds, when they dissolve, if they're soluble, break apart into ions, where molecular compounds, if they dissolve, they don't form ions. They stay as neutral molecules. So that means ionic compounds, when they dissolve, can conduct a current because a current requires ions, charged particles in the solution to have the current pass through it. So we use the term electrolyte to describe something that, when dissolved in water, produces ions, so therefore it can conduct a current. So soluble ionic compounds are electrolytes. Insoluble ionic compounds are not electrolytes because they're not dissolving. And all molecular substances are non-electrolytes. So only soluble ionic compounds are electrolytes. So I could ask something about that. Okay, let's get started on the problems. Let's skip all this. I'm not going to do sort of that deep history of all the stuff they did before. We'll skip that. But I said, I don't know if I will. Again, I'm not being coy. That's probably the 8th time I said coy in these video lectures. I don't remember exactly what's in the final because I didn't want to look because I don't want to give away things. I'd kind of like, if I knew what was on it exactly, I'd be tempted to tell you, okay, don't know this exact question, but know this exact question. So I'm trying not to look. And plus, I might do a little editing for this. So this is one thing that I think people know anyways, the Rutherford gold foil experiment. So if I ask something from kind of the history of the atom itself, not quantum theory, it's going to be on the Rutherford model. So the whole idea is Rutherford shot alpha particles, which we later found out are helium nuclei, because we learned radioactivity a little bit later, at this thin gold foil. And what did he discover? Well, first of all, what did he think? He thought that because of the plum pudding model, where the mass is all spread out into a huge volume, there was nothing dense enough to deflect this high-speed little bullet, this alpha particle. So he expected all the alpha particles would go straight through without being deflected. But what he discovered was, and I've asked this before, so I think you're used to it, that a few of the alpha particles were deflected, but most made it straight through. a lot of people think it's A, that, no. Because, this whole thing allowed him, what's at number 11 here and number 12, I'll just kind of get to it, is that led him to propose, if only a few alpha particles bounce back, there must be something super dense and positively charged at the center, and then the rest of the atom is all spread out where the electrons are. So you have like electrons kind of far away, and then you have this really tiny nucleus at the center that has most of mass and all the positive charge. And that explains the observations, because the alpha particles mostly are going to go straight through the atom, but occasionally one is heading right at it and it'll bounce back at a weird angle. So that was his model, his nuclear model, as Rutherford with his gold foil experiments. So if you get that idea, you probably don't need to write it down. It's going to be something along those lines. Okay, 61, again, skipping some of that sort of deeper history stuff. That, and then I'm not going to, that you could read that one in 61 and redo them. I'm not going to do it again here. And for number 4, I circled it. Just know that if I ask something about this, for the quantum theory, associate Planck with this. That was the answer to this one. I know it wasn't much of a question. I did most of the writing, but I just wanted to kind of get you to understand what the basic idea of quantum theory is that quantum theory says that certain properties on a microscopic level could only take on certain values and not the in-between values. The values are incremental. So for example, maybe the vibrating thing could have energies of 4, 8, 12, 16, 20, 24, but it couldn't therefore vibrate with 9 units of energy or whatever. Okay, so that's all you would need to know. So here's that idea about thermal radiation I mentioned. And again, I'm probably not going to ask this. I can't waste a question on this. And I didn't spend more than just 10 minutes talking about it, and I think one homework question about it. So let's just go ahead and just skip that. And hopefully I will not put it, if I do put it on the test, if I just said I'm skipping it, and I don't remember, and I do put it after the final, come find me, and then I'll give everybody that point back for free. So this is the photoelectric effect thing. The guy who proposed the solution to the problem was old AE, Albert Einstein. And he proposed, to explain it, he said that light can behave like particles, which we call photons. I'm not going to ask a question probably about that, but it just so you know the effect, or the name. So here's the idea of the photoelectric effect. I got to read this question to see if what I'm explaining. Sorry. So actually, I'm going back far here. The blue photons might kick off which subatomic particles from the surface? Electrons. I'm not sure why I'm asking that. That's why I was reading that. It's like, what am I asking there? But the amount of kinetic energy that those kicked off electrons get depends on how much energy the photons have. So what they found, again, I'm trying to read the question because I'm trying to explain the thing, but I also want to respect the question, so I'm answering the question. I'll just go ahead and read the question, darn it. What did they find out that caused the electrons to be kicked off with more kinetic energy? It wasn't how bright the light was. They thought that bright light meant more energy. That was what I wanted to explain a moment ago, is what they expected was the brighter the light, the more energy the electrons would have. But what they found out was, no, it didn't have to do with the brightness of the light. Just by increasing the frequency of the light from, let's say, blue to UV, then the electrons that get kicked off would have more energy. And that was kind of a surprise to them. Like, what does frequency have to do with the amount of energy that's going to be given to the electrons that get kicked off? But that's what they discovered. So that's why Einstein proposed that the energy of a photon is related to its frequency. It sounds obvious now because we do problems with that. But at the time, no one proposed that the energy of a photon, or even that there were photons, is just directly proportional to the frequency of that type of light. So just as a reminder, you should be able to order these things based on their type of radiation in terms of energy, where on the Roy G. Biv, for example, the V side has a higher energy. And for the RMI VUXG, the G or the gamma ray side has the highest energy. So ordering those from the lowest energy to highest, the lowest would be IR, then blue, then UV. So which photons probably won't have enough energy to knock off any electrons? The IR. They have too low energy. They have a small frequency. Which photons have enough energy to kick off electrons, but barely, so they don't get kicked off with much energy? That'd be the blue. But the UV, those have a higher frequency, so they have more energy per photon, so they can kick off the electrons. Again, I don't know why I just spent 3 minutes explaining that. It's unlikely I'll ask it, but there's a chance. So don't get mad at me if I do put one on the final about that. I'll do one more below, just because I kind of butchered my initial explanation there. So yeah, this is going back to Roy G. Biv and RMI VUXG. Let's order them from lowest to highest. So let's find it. So probably radio is the lowest. So I'll put 1. 1 meaning lowest here. 2 would be microwave. 3 would be the visible light, but orange is lower frequency than blue, so blue has a higher energy. Then we get to UV, which is a little bit higher than blue, because you go blue, violet, then UV, and then X-ray is the highest. And then lowest frequency to highest frequency would be the same. And then shortest wavelength to longest wavelength, so be careful. Shortest wavelength is going to be backwards because the shortest wavelength is gamma, but of the list I showed you is X-rays. So that'd be the reverse of the last two. Okay, I'm going to hurry up a little bit. So this is when we're going to be using equals HF, which you're going to have to use for probably a couple times on the test. The reason why I'm drawing an arrow to 10 is more likely I'm not just going to give you F and have you calculate E with this equation, or I'm not going to give you E and have you calculate F with that equation. It's more likely to challenge you a bit is I'm going to give you, for example, like this problem, the wavelength. Sorry, this thing is jumping around like crazy. I'll give you the wavelength and say what is the energy. So the way we did this, I'll just go ahead and show you the answer key just to save time. There's not much explanation in this, so I don't need to really explain it as I'm writing. But the way I think I initially did it was just using C equals lambda F and E equals HF individually to solve it. But as I'm telling you, you have a cheat sheet. So yes, you can write E equals HF if you want to go from F to E or E to F. And you can write C equals lambda F to go from C to, I'm sorry, you don't go from C, that's given to you. Go from lambda to F or F to lambda. But we combine those to form these equations. E equals HC over lambda, or lambda equals HC over E. So that's how we go directly from energy to wavelength, or from wavelength to energy. So write all 4 of those down and you don't have to do it. And then this one is just B is just the backwards of A. So here I'm giving you the energy and we want to know lambda. And yeah, make sure you understand when I'm saying wavelength, that means I'm looking for lambda. Write that down on your cheat sheet if you don't know what that is. Okay. And F is frequency, C is the speed of light, which I'll give to you. H is Planck's constant, which I'll give to you. So if you don't know what those are, look on the list of given information. So like I said, let me show you the answers just so I don't have to do it. So again, this is just simply using equals HF or solving for F. But again, more likely, for sure, I'm going to do it where you have to do both. So as you can see here, to go from the wavelength to energy, I first did it in 2 steps. I used this to go from the given lambda to the frequency. So I solved for F here. And take a look at that. Make sure you understand how units cancel and whatever. And then once I have the frequency, I can use the Einstein's equation for the energy of a photon with the given Planck's constant to solve for the energy. But I said, hey, why not just use this combined equation here? And we just plug in H and C and lambda, and we get the energy. Now, that said, be careful. I don't necessarily have to give you meters. I could have said that this was 1 nanometer, and you would have to know, because remember, I'm not giving you the Greek prefixes. You have to know that represents a billionth of a meter. So if we're going to be using joules and seconds and meters and seconds, your lambda has to be the SI unit in meters. So make sure that whatever I'm giving you for the wavelength, you convert it to meters. And then for B, it's just the opposite. This time I'm giving you the energy, and I want to know lambda, the wavelength. And again, the first way I did that is, well, if they're giving me the energy, I could use Einstein's equation to solve for frequency. And then once I know frequency, I can use this equation to get lambda. Okay? And if you want to see how units work out, remember that Hertz, which I found right there, is the same thing as a cycle per second, or just simply 1/2. So we get things canceling. But again, it's a little bit easier if you write this down to use lambda equals hc over E, and you just kind of in one step get the answer. And also remember, I might not give you energies in joules. I might give you, which is frequently for like Bohr atom problems, attajoules. And if I do, I will tell you that an attajoule is equal to 10 to the negative 18th joules. And then you would use a conversion, because we would want to use joules in this problem, so we'd cancel the joules from Planck's thing. Okay. All right, let's move on. We got a lot more to do, so I'll try to hurry a little bit. I won't do this one. I just wrote that, redo it, that's 62. Again, as I said at the top of this video, there are a lot of questions that kind of repeat. So you're going to see for these last, 8 problem sets, a lot of these same problems. Even for this one, the idea that we say the problem, I'm not going to ask you this, but just so if you run across the term that's quantized. And I said I'd do this again, so let's do that so I will explain it a little bit better. Consider the following types of light from lowest to highest energy. In the photoelectric effect, which of the 3 is most likely unable to kick off any electrons? The lowest energy one, IR. Which is most likely to kick off electrons that are given the most KE? The highest energy ones, UV. So 3, it says, for part A, if you made the IR light brighter, but kept the frequency the same, would it then be able to kick off electrons? No. It's not about the brightness, it's about the frequency. So IR is just not good enough. Hopefully you said UV for part B. If you made the UV light brighter, but kept the frequency the same, what would it do? Well, it would eject more electrons, but on average, those electrons wouldn't have any more energy. It's just that a brighter light just corresponds to more photons. And then that's photons. So yeah, that didn't take too long. All right, so let's see what else. Okay, so now we get into spectra. I'll try to hurry up a little bit. I keep saying that, but I never do I? Sorry. Here are 3 spectra. Let's identify them based on their appearance. Absorption, emission, or continuous. So label each for each one of those. This is the continuous. You get all the different colors of the rainbow. This is the absorption, where it looks like a continuous, but some colors of light got absorbed, thus the dark lines. And this is the emission. So do little drawings on your cheat sheets, and so you know which is which. And then also write down these follow-up questions. Which one is produced when you heat up a low-density gas? That's going to be the emission spectrum. So that one over here. Which one is produced when you pass white light through a cool gas before you look at the spectrum? The absorption, because the gas is absorbing some of those photons from the continuous spectrum. And which is produced when you heat up a dense material? That's the continuous. Terminology, I'm not going to write these down, but just repeating it. The orbit closest to the nucleus is called the ground state. Higher orbits are called excited states. For an electron to jump from a lower energy level to a higher energy level, it must absorb a photon. When the electron falls back down to a lower energy level, it will emit a photon. And as I said, depending on the teacher, they call these orbits or energy levels or shells, things like that, which we talked about later. Go back to the earlier question on spectra. Which one is produced when electrons jump from lower energy levels to higher? Well, that sounds like an electron absorbing a photon to be promoted to a higher energy level. So that's the absorption. Which one is produced when electrons fall back down to lower energy levels? Well, it's falling back down and in the process releasing a photon. That's the emission. So kind of know this and this as far as follow-up questions for the 3 types of spectra. Now, there are a bunch of questions like number 10, where the whole Bohr idea that the atom could absorb or emit photons corresponding only to those energy differences between orbits. So just let's go through this really quickly. And then again, attajoules, 10 to the negative 18th joules, if we ask about it. I don't think I do here. What is the energy of the ground state? Well, it's 0, even though when you get older and you look at true Bohr atoms, it's defined differently. What is the energy of the second excited state? Well, the second excited state is that one. That's the first excited state. That's the second excited state. I shouldn't put 1 and 2 because the ground state is, I'll put that, is actually n equals 1. That's how we abbreviate it. And so n equals 2, the first excited state is the 4 attajoule state. Oh, I'm sorry, it's asking for the second excited state, 7 attajoules. Okay, so that's the second excited state. Can the atom absorb a photon of the following energies? So as long as there are 2 orbits that differ by that energy, it can absorb it. So 7, yeah, because it can go from 0 to 7. 3, yeah, it can go from 4 to 7. 6, probably not, because the first 2 were yes. I don't see any 2 orbits that differ by 6, right? So that's yes, yes, no. Draw an arrow that shows from which orbit to which orbit an electron must move when a 5 attajoule photon is emitted. So if it's emitting a photon, the electron must fall down to a lower energy level by losing, just getting rid of that, by losing energy, by falling down to a lower energy level, it's going to emit a photon, but it needs to be 5 attajoules. So it's going to be this. So when the electron makes that transition, the electron or the atom has lost 5 attajoules, and so out comes a 5 attajoule photon that's being emitted. Okay. Hey, good news, as I told you earlier, we won't worry about that. Now, I won't do these, maybe I'll do, yeah, in fact, I won't do them, but I'll just point them out. This was review of stuff that we did in the previous unit, because again, 2 things here. It comes up again for stuff that we're learning, but I think these problems were still before, I think they were like, I guess, but still on the test or something that was coming up, because some of these problems were overlapping 2 tests when we were kind of about to do a test and then get into a new topic. But anyways, I'll let you read those, just some review things about the difference between a metal and non-metal. I talked about that last video, and parts of the periodic table, knowing the names of them, which ones forms what kind of ion. So make sure you know all that for the final. Just trying to save time. 63, same problems, but hey, let's do it again. The left spectrum shows an absorption spectrum. It is produced when the atoms absorb photons. As a result, electrons go to higher orbits. How is it produced? By passing white light through it, and through some gas, and that gas absorbs some of those photons, knocking electrons up to higher orbits. And of course, these are going to be all the opposites. The right one shows an emission spectrum. It's when atoms emit photons. That happens when electrons fall to lower states, and it's produced by energizing some gas, either by heating it or running a current through it or something that causes the this process to happen. I won't do 2, it's just another repeat of, hey, can it absorb this number of attajoules, or could it emit this number of attajoules? So again, you're just looking for yes, anytime there are 2 that differ by that energy. So maybe just to do 2 of them, I'll just randomly choose 9 attajoules. Well, yeah, because there's a 9 and a 10, so it could absorb or emit a 9 attajoule. But what about 17? I don't see any 2 that differ by 17, do you? So that's a no. So anyways, that's all I'll do. 3 is similar to that. But let's do one of these. There'll probably be some question like this. Again, it's only going to be worth 1 point, but I could be like a point plus some follow-ups. As you can see, there are a bunch of follow-up questions or different things I could ask. So let's try this one. This one involves, let me just erase what I just did so it doesn't confuse our luck, is this one involves giving you the energy of the transition and then asking for the wavelength of the photon associated with it. So let's go through the whole thing. I'll slow down a bit and not talk so fast. So it says, shown are the energy levels of a Bohr atom. An electron jumps from the n equals 5, or 4th excited state, to the n equals 2, or 1st excited state. Okay, so it's falling down. Will a photon be emitted, or will a photon, meaning a light ray, need to be absorbed in order to make that transition? It's going to be, where's emitted? There it is. Emitted. So when the electron falls down, the atom is losing energy. So as a result, it will release that energy in the form of a photon, which we often just use Okay, it's not writing out at all. Like a little gamma to represent generically a photon. I know that's also the symbol for like a gamma ray, but often for a photon, we just use gamma. What will be the energy of that photon? So look at the energy levels. So if the electron loses 1.1 attajoule, right? That's what the electron did. It has to get rid of that 1.1 attajoule. So the photon will have an energy of 1.1 attajoule. So that's how you find the energy of a photon. It just corresponds to the energy difference of the two orbits that involved in the transition of the electron. So let's do the numerical part of this. And let's use those two equations instead of doing it in two steps. And write these down. So we'll either use E equals hc over lambda, or we'll use lambda equals hc over E. We're going to end up using that second one. So I'm giving you what an attajoule is. I'm giving you H, and I'm giving you C. So we have everything we need to know to find the wavelength. Just make sure when I say find the wavelength, I'm saying find the lambda. So let's use that second equation. I'll go ahead and show my work here. It's hc, so we do 6.63 times 10 to the negative 34th joules times seconds. C is 3 times 10 to the 8th meters per second. That's going to cancel the seconds. And we'll have joule meters right now. And then we just divide by the energy. But I can't put in 1.1 attajoule because we're in joules now. I need my numerator to be in joules in order for the joules to cancel. So remember that in attajoules, 10 to the negative 18th joules. I would give that to you. So I have 1.1 times 10 to the negative 18th joules. And then the joules cancel, and we're left with meters, which is what we want. And I'll see what the answer is as I scroll down. So that's a classic, absolute classic question. So probably something on the final like that. I'm not going to redo these. I just said still know these things. Again, things from the previous units. So you feel free to, again, go over all the homework and make sure you know these. Write them down. So just as an example, you better know calcium's +2 and gallium's +1. I'll just do them. 0, it doesn't form an ion, right? -1, +1, -2. All those things. And then, you don't need to know this. Okay, let's go to 64, because I think this goes up to around 70, but then there's some beyond this, but we start to overlap with the next test. Okay, we want to do sort of that history. And so a lot of these also are repeats because, we won't bother with that one, because I think this was happening when we had like spring break or something, and we came back, and I just wanted to review a bunch of stuff that you might have forgotten. This we've already done. I'm not saying exit out. That's, you need to know that, but it's just another thing like we've been doing. You don't need to know that. This is the same problem. We're given the energy. In fact, how is it different? I guess it's the same one. Maybe I made a mistake. I meant to do the one where it's backwards, that I give you the wavelength and you find the transition, but that comes later. So it's actually very similar to the one we did. I think the only difference is I was doing specifically the hydrogen atom, so giving you real numbers for the hydrogen atom to figure out, what whichever line that is. I think this one right here, we're looking for what the wavelength of that is. There's more review I'm not going to go over. So this is, if you're curious, homework 64, things you should know about metals versus non-metals. And the rest of this, I think, is just all review again. Now, we get to new stuff here. We start talking about compounds and elements and ionic compounds. This is very simple. It's just like the ones that are just made up of one element, those are elements. The rest are compounds. Now, I will ask you things like 13 and 14, but we're gonna see them later on these problem sets. So we'll just do the later ones. All right, let's get to this. This is a little bit different, I think. Let's see. Yeah, so this is just backwards. So I could ask it backwards where I'm giving you, as you'll see, the wavelength, and we want to know the energy of the photon. The previous one was I gave you the energy of the photon, and we want to know the wavelength. So here we are with another Bohr atom, and notice I don't know the energy of this one. So we're going to end up trying to find the energy of that n equals 5 orbit. For an electron to make the transition shown, will it need to absorb or emit a photon? It needs to absorb. Absorbing a photon causes the electrons to go to higher orbits. That is going to be a classic, probably something I'll ask in the multiple choice section when I'm doing a problem like this, kind of follow-up questions or whatever. When the electron makes the transition shown, it absorbs a photon of that energy. In other words, there'd be a line in the absorption spectrum at that wavelength. We can use this to find the energy of the n equals 5 energy level. Find the energy of the photon, and then again, let's just use that nice one. Okay, so I'm not gonna actually plug it in this time. You plug in the H and the C, but for lambda, I was nice and I gave you meters, but again, understand that if I give you like nanometers or micrometers or something, convert that to meters. And just to see what the answer is, and then we're gonna convert it to attajoules so we can compare it to the attajoules here. Let's just see what the answer is. We'll move down here and see what the answer is. Where is it at? Oh, right there. Okay, so you plugged it in and you got this, which represents 0.6 attajoules. Now that's the energy of the photon that was absorbed. So this energy difference is 0.6 attajoules, that energy difference. So this must be 0.6 attajoules higher than that, or in other words, that's 2.1 attajoules. Okay, so that's how you do that problem. Okay, let's go back to the ones without the solutions. What else was I gonna do? Okay, here's something. This is again something I'm going to ask somewhere, I'm sure. Identifying whether something's an ionic compound or molecular compound based on what makes up the formula. So whenever you just see nonmetals, it's molecular compound. Whenever you see a metal and a nonmetal, or, not that I've introduced it here yet in these problems, a polyatomic ion, it's an ionic compound. So O and F are, so I didn't circle that, O and F are nonmetals, so that's molecular. Calcium's a metal, fluorine's a nonmetal. Copper's a metal, oxygen's a nonmetal. Sulfur and chlorine are both nonmetals. Simple, right? 4, I'm not going to do all of these, but this is just the idea that if you write the formula of an ionic compound, for example, between a metal and a nonmetal, we just write the empirical formula, the lowest whole number ratio. There's no need to write unnecessarily big numbers. So you shouldn't write Ca3O3, just write CaO. Or it shouldn't be Ti8Cl32, it's just TiCl4, and so on. All right. I think I circled ones I wanted to go over. Then tons of these throughout the problems. You're gonna see these over and over. Get good at them. I'm gonna ask you a question or two about these. So coming up with the chemical formula of an ionic compound made between these two things. I'm just going to do a few of these. I'm not going to do them all. In fact, there are more down here in number 8 and more later. So what you do is you say, well, what charge does aluminum like to form? Well, hopefully you already know, or figured out, it forms 3+, and bromine, a halogen, forms -1. So I need them to be neutral. So what's going to be the formula? AlBr3. Cesium, we don't use it very often in the problems, but that's an alkali metal, so it's +1. Oxygen's -2. So it's going to be CS2O. We'll keep doing it. I'll just do them. They're pretty fast. Strontium, you might not know this, but it's an alkaline earth metal. You would find it in the second column. So now you know it's +2. Oxygen's -2. So we get SRO. And I don't know, we'll just gotta skip that. It's fine. What about 8? Is that any difference? I think it's just more practice, but I just wanted to point out this one here is that we don't write, we know that AL is +3 and that F is -1. So we need 3 Fs, but you don't write F3AL. You always write the metal first. That's the tradition. You don't need to memorize the polyatomics. They are in the solubility table. I'm just making sure that by skipping this, I'm not doing anything. I didn't do a 2 to 3, so let's do one of those. Let's go back and maybe do gallium and sulfur. You would find gallium underneath aluminum, so we're going to assume it's +3, and sulfur's -2. So you've done enough of these, right? We're going to get Ga2S3. You can do those in your sleep now. Yeah, and a lot of these, again, they're going to be repeats, or there are things that I'm not going to ask because they involve drawing a diagram or something. Okay, what did I say here? Or, you don't need to memorize them. They'll be given to you. More practice. I'm not going to do all of these. These are just now practice where some of them might be polyatomics. Again, coming up with the formula. I'm going to skip some. Let's see. Let's try this. Ammonium and sulfur. Ammonium is NH4+. It's in the solubility table. Sulfur is 2-. So we need 2 ammoniums for every sulfur. Okay. What's another one we could do? We'll try this one. We'll do barium and carbonates. Is that good? No, that's too easy. That's just going to be BaCO3. We'll do magnesium and phosphate. The old 2,3. Magnesium is an alkaline earth metal. Phosphate is PO4 3-. We're going to get Mg3, PO4 2. Notice the use of parentheses. I hope you don't mind. I'm not doing all of them. I mean, you got the answer keys. You can look at all of them. And again, that doesn't mean I have 3 chromiums. It's just telling me that chromium is charged +3. Anything there? No, just, again, more practice there if you want to do some of those on your own. Probably not a lot more time here, so hang on, because, again, a lot of this is just going to be repeat. As you can see here, more repeats. I'm not sure what was going on here. I'm sorry that I made you do all these homework problems, but I hope you felt that it was good for you, that you learned this really well. I'm just seeing if there's... Yeah, so this is what I was talking about, where I'm not going to ask you a question like this on the final, but I'm hoping it helped you understand that if you have, for example, Na2CO3, that it's not made up of a couple of Na atoms and a carbon atom and 3 oxygen atoms. It's made up of a 2 sodium ions and a carbonate ion. So by doing those visual things, I think it helped you understand the real constituents of ionic compounds. We've done something, and again, these are just more problems where you're finding the formulas. Not too hard, right? I'm just seeing if there's anything kind of tricky, but I think they're fine. You should know how to do this. 11 is just finding the charge of the metal. So if oxygen's -2, magnesium must be +2, right? I'll try to do some different ones that are a little bit harder. Each oxygen is -2, but I have 2 oxygens. So altogether, those 2 oxygens are -4. So what must be titanium? +4. Let's do this one, which is a little tricky. Each phosphate is what? -3. But I have 7 phosphates. So altogether, the phosphates give me -21. So the 3 manganese must give me +21. But what's the charge of each manganese? +7. Okay, I think you get the idea. Now, I'm going to do this a little bit later, some of these, because they're kind of funky ones, because I was intentionally, remember that was the homework 6, 7. I was just doing some funky ones that involve 6 and 7. I couldn't quite get this one to work with 6 and 7, so number 13. So we'll see some like that in the middle. So yeah, molar mass is just, you sum up the masses of all the elements that make up that compound. So calcium, if you look in the periodic table, is 40.1, and each fluorine is 19. So that's 38 for that. So the molar mass is 40.1 plus 38, so that's 78.1 grams per mole. Okay, now I just skipped that one, and we can do that on your own. I'd say for a hint for that one, I would find out what the mass of NO3 is, and then go ahead and multiply it by 3, and then add your aluminum. So now let's, again, practice. Maybe I'll do a couple of these, and make sure you write these down if you're not an expert, the method of how you do them. The numbers can change, but the method's the same. So we're given that we have 6.5 moles. And now we're going to use a conversion factor. Again, think of that as something over 1, where I'm using the molar mass. And always one side is going to say 1 mole. And the other side will say the actual numerical mass in grams. So I'm trying to get rid of moles, right? I'm trying to get as my answer grams. So I need to put the 1 mole on the bottom so that the moles cancel. And then I put the 78.1 on top. And again, I'll look at the answer key below to see what it is. That's how you do that one. Now the other one, I have 40 grams of calcium fluoride. Again, what you use for your conversion factor to go between grams and moles is you use the molar mass. This time I want to cancel the grams, so I put the grams on the bottom, and always one side will say 1 mole, not 78.1 moles or whatever. Now again, those cancel, and the way I wrote it makes it look like they won't, but please just remember, that's always something over 1. So if I'm trying to cancel that gram, I need to put grams on the bottom, and that'll give me some number of moles. And again, I can, as we flash by to the next problem set, we can see what the answers are. So know how to do that. There'll be only one problem, but make sure you get it. I went ahead and did a few more of these. We probably don't need to do 5, but now that we have these polyatomics, let's go ahead and find the chemical formula. We're about to get to naming. So what's a good? We'll do lithium and sulfate. Again, the method is you say lithium is +1, it's an alkali metal, and sulfate is the 2- ion. So we're going to need 2 lithiums for every sulfate. And I don't need parentheses here. You only use parentheses if there's more than one polyatomic ion, not more than one monatomic ion. Let's do ammonium and phosphate. Ammonium is NH4+. Phosphate is PO4 3-. So I'm going to need 3 ammoniums per phosphate. Okay, you get the idea. Well, we'll do one with the Roman numerals, sorry. We'll do vanadium 6 and carbonate. And raise your hand if you, during the final, if you don't know what a Roman numeral stands for. I don't want to penalize you for that. So that means I have vanadium 6+ and carbonate 2-. And so I'm going to need 3 carbonates per vanadium 6+. Hopefully that makes sense. 5, I won't redo those. And then here's some more things that involve redrawing things and just again hoping to improve your conceptual understanding of chemistry. So let's get to some naming. And so naming, as I did my little lesson earlier, to make it sound simple first, for ionic compounds, first of all, you are not saying di, tri, tetra, penta, whatever. We're just going to name the first elements, name the second elements. The first element's always the cation. But here are the 2 special rules. If the second element is just a monatomic ion, it's not one of our polyatomics, you end it in "-ide". If it's a polyatomic, you don't change the name. And then the other special rule is if it's a metal, the cation is a metal that can have different charges, we need to indicate its charge with Roman numerals. And as I said on these, or somewhere here, I didn't put that type on this because this was, I think, before we... No, I guess we did. Maybe we did do it in class. So anyways, let's just name these. That's sodium and sulfur. So we have sodium. You just always say the first one. And notice that's just a monatomic ion. So we change the ending to "-ide". I don't use sodium 1 because we all know sodium is +1. It's an alkali metal. That's calcium. We don't need to say calcium 2 because we all know it's +2. And that's a monatomic ion. So we change it to "-ide". The fact that it's a 2 doesn't mean it's a polyatomic ion. It just means we have 2 Br-1 ions. And I won't keep writing this, but that's going to be aluminum oxide. We don't say dialuminum trioxide. We don't use those for ionic compounds. Write that down in big letters if you think you're going to screw it up. I'm going to try to catch you on multiple choice using the wrong naming technique. And that's going to be gallium fluoride. Okay, now let's name these. Now we have some polyatomics, so we don't change the ending of polyatomics. So this will be, I'll write it out first, and I'll just go ahead and say aloud the rest. Sorry, my pen just does not work as well as my Apple pen. Magnesium carbonate. Notice I did not change that. Sorry. To carbonide or something. That's going to be calcium nitrate, not calcium nitride. Nitride is the negative ion of nitrogen. That's ammonium phosphate, not ammonium phosphide. Phosphide is P3-. And that's aluminum sulfate, not aluminum sulfide. Sulfide is the S2- ion. Okay. And again, don't say di, tri, or whatever. So finally, here's the last type, and there are going to be plenty of examples to come in the next problem set, so you will not run out of sample problems to do. So if the metal, the first element, is group 1, alkali metal, group 2, alkaline earth metal, or group 13, boron and aluminum's family, we don't write Roman numerals. But again, for this class, every other metal we're going to write Roman numerals because typically the rest are going to form different charges. So nickel, that's not group 1, group 2, or group 13. So we say its name still, but we need to indicate what its positive charge is. Well, what's the charge of each chlorine, which is a halogen? -1, right? And we have 2 chlorines. So the 2 chlorines give us -2 altogether. So what must be the charge of nickel? +2. So we say nickel 2 chloride. It's a monatomic negative ion, so we end it in -ide. That's silver. It's not group 1, group 2, or group 13, so we're going to use your Roman numeral. What's the charge of nitrate? Recognize that as nitrate, not as an N and 3 O's. Well, nitrate's -1, so that must be silver +1. So we say silver 1 nitrate. ZrO2. Well, oxygen is -2 each, so 2 oxygens give me -4. So what must be the charge of zirconium? It must be +4. So we say zirconium 4 oxide. So again, the Roman numeral is not how many you have, it's what the charge is of that metal that precedes it. So zirconium 4 means zirconium is charged +4. And that's lead. Each sulfur is -2, so the 3 sulfurs are -6. So the 2 leads are +6. So what is each lead? +3, right? Sorry, I went kind of fast, but I think you guys are really good at these. So that's lead 3. Oh, sulfide. I so often do lead 3 oxide. Here's one where I did sulfide. Okay, let's see what's left. I think we're getting towards the end here. Oh, and I think I said I'd show you the answers, but yeah, here are those things again where if you're in moles, you're going to put 1 mole on the bottom, and that's going to give you grams. If you're in grams, you put grams on the bottom and 1 mole on the top, and that gives you moles. So again, if you think you're going to not remember how to do that, write down a sample problem. And if I ask you that, or when I ask you that on the final, you can look to see whether you're multiplying or dividing by the molar mass. You just have to make sure you find the right molar mass. All right. There's something with the diagram I do want to point out. I guess there's these questions coming up, but I won't redo this, but go ahead and look at the answer. Oh, I'll just show you the answer key just to remind you. We find the molar mass by adding up all the elements that make it up. Okay, make sure you can do that. And then here we go again. If we have a 1/2 mole and the molar mass is 180 grams per 1 mole, we're going to multiply by 180 grams. If we're in grams and we want moles, we put grams on the bottom and moles on top. Okay, so make sure you know. Again, it's only one question, but it's something we haven't practiced in a while. This is something I do want you to know. I'll probably ask some question variation of this. I want you to understand this. I think it shows good knowledge that someone, of your age who's just learning chemistry can understand this. I mean, even like sometimes my sophomores at my old school, they just don't quite get this. And I think by taking a lot of time and doing all these diagrams, which I never did in my old school, I think it's helping you understand this. So Al2CO33 means you actually have 2 Al3 plus ions in that compound, and you have 3 CO3 2 minus ions. So that's what it is. It isn't some kind of Al2 molecule where you're 2 bonded to each other, and you don't have some kind of CO3 thing. It's just we have some ions that make it up. Okay, let's do some of these. We're going to name these. We just did some, right? I'm losing track here. Yeah, we did. But let's just do a few of these just to practice. So tungsten and oxygen. So W is tungsten. And is it group 1, group 2, or group 13? No. So we need to write its charge. Each oxygen is -2, so that's -6. So tungsten must be +6 here. Oops, I need to write a V and an I. So tungsten 6 oxide. We change it to ide. It'll be easier because it's multiple choice, but be careful. Don't circle tungsten 6 oxygen or something. Okay. I'll just say them aloud. That's sodium sulfate, aluminum iodide. Maybe we'll do a couple others. That's ammonium hydroxide. Recognize that as ammonium and hydroxide. That one, let's try that one. Each phosphate's -3, so that's -6, right? So the 3 cadmiums better be +6. So what is each cadmium? It's +2, right? So that would be cadmium 2 phosphate. I did that right? I'm doing it really fast, so that'd be -6 +6, yeah. Write the chemical formulas. I'll just do a couple of these to remind you. We did a bunch of these. It's pretty much like the original skill we did where I said, what is the empirical formula for these 2 things? So let's try, I don't know, we'll do D. Chromium 5 means you have chromium 5 plus. That's what the V means. It means the chromium is charged 5. It does not mean I have 5 chromium ions. And hydroxide's OH minus. So that's going to be CrOH5. What about, we'll do this one. Well, another chromium. Sorry, kind of boring. Chromium 6 phosphate. That means I have chromium 6 plus this time. And phosphate's PO4 3 minus. So I need 2 phosphates. That was 2. I just said 2 and I wrote 3. Okay. Look at more if you don't know how to do those. All right. Let's look at these. Vocabulary, if it comes up. If a solid can dissolve, we say that it's soluble. If it cannot, we say it's insoluble. You dissolve salt in water. The salt is the solute. The water is the solvent. And the salt water that you make is the solution. Okay, again, this pencil is not great. If a solute dissolves specifically in water, we call it an aqueous solution. I'm not going to waste a whole question on this, but that term might come up. Now, I drew 11 just because I think there will be something. If I remember, it might already be there, but if not, I might add something. Or just kind of maybe in a multiple choice or something, identifying or interpreting what's going on. So if something is soluble, maybe I'll just point out this one here, number 10. If something's soluble, and I should say an ionic compound is soluble, it'll break apart into its constituent ions. So this is my soluble ionic compound, QZ, because it broke apart into ions. It's an electrolyte. It can conduct a current now. XY is insoluble because notice it just fell to the bottom and they're all still stuck to each other. It's just going to be a solid that fell to the bottom. So here I said, I think I told you just assume that they're soluble, but we just want to draw what it looks like. So yeah, I know magnesium chloride is soluble. So it's going to form what? An Mg2 plus ion and a couple of chloride ions. Not some kind of Cl subscript 2, but it's going to have 2 separate chlorides. Again, it didn't seem to be that important for what we're doing, but I think foundationally speaking, understanding that, helps you understand chemistry better. Aluminum nitrate will be an aluminum 3 plus ion floating around and a few nitrates that are separated. Doesn't have to be boxes. I just did it that way. It was easier to draw them and get your things in there. And then this one, I said, let's say MgF2 is insoluble. What would it look like? Well, I kind of gave it away over here, I think, and I guess I didn't. Not quite the same one. You're just going to have an Mg2 plus stuck still to F minus and F minus on the bottom. They never dissolved, so it just falls to the bottom. It's not a solution. They have to dissolve to form a solution. Okay. 70. We are getting near the end. In fact, you're seeing I didn't circle many here because, again, more practice if you need it. So I don't think there's anything here. Let's do a little bit of solubility. I'm going to, unfortunately, I don't have the chart right here next to it. I can flip back, so I'm not going to remember those. I should have printed this out so I can say them aloud. But let me just go back to the solubility table and show you how you use it. I'm not going to give you this. You have to know how to use it. So if the way to figure out if something is soluble is for that ionic compound, find the anion in this column. And if the cation that's bonded to it is in this one, it is soluble, meaning it will dissolve to some extent. If the positive ion is either in this column written or it's kind of implied by, for example, saying all other ions, it's insoluble. It will not dissolve. So let's see if I can remember. I have you can't believe how bad of a memory I have. So I'll see if I can remember maybe 2 of them by the time I flip to the other table. So let's try, we'll try these 3. Let's see if I can memorize 3. Calcium fluoride, potassium nitrate, sodium phosphate. I'm not even kidding. I just have such a bad memory. That's why I could never do well in biology. I can't remember anything. Calcium fluoride, potassium nitrate, sodium phosphate. Okay. I've already forgotten. Calcium fluoride, I remember, is the first one. So let's try that one. Fluoride's here. Where's calcium? I'll write them down. I forgot the third one already, but potassium nitrate was the second one. Calcium fluoride. So there's fluoride. Where's calcium? Well, it says it's soluble with all positive ions except, calcium. So that's insoluble. What about potassium nitrate? You find the negative ion, which is right here. Where's potassium? All positive. Oh, it's soluble with everything. And that's what I told you, that if you, one kind of cool thing to remember is all nitrates are soluble. All alkali metals and ammonium ion compounds are soluble. So anyways, let's do a couple more. I'll try to remember. I'm serious. My memory is just not good. Sodium phosphate. I'll skip that one because all alkali metal ones are soluble. Let's try magnesium hydroxide. We'll do that one. MgOH2. So find OH, that's the negative ion right here. Now, where's magnesium 2+? Well, it's soluble with alkali metals and ammonium and barium, but I don't see magnesium. So it's implied that magnesium 2+ is over here. So therefore, it's insoluble. Okay, so I'm giving you the solubility table. You should be able to figure out if it's soluble or not. Okay, and these are things I'm not going to, molarity. Sorry, I wish I had kept it up and we got into pH and stuff so we can see where we use molarity, but it's nice that you learned it. Is how many moles are dissolved per liter. You're going to hear that a lot in chemistry in sophomore year. 71. I'm not going to do many of these, but at some point you should understand conceptually how to convert between grams and moles without a conversion factor. So if I have 3 moles, think about this logically, and the molar mass I'm giving you of sodium hydroxide is 40 grams per mole, okay, dramatic pause, what is the mass of that? 120 grams, right? Because it's 40 grams per mole, and I have 3 moles. So we multiply. If we're given moles, we just multiply by the molar mass. That's all we do. Same thing here. We just multiply 5 moles by 20, and you get 100. Multiply a half times 28, you get 14. So it's nice that you just know that whenever you have moles, you just multiply by the molar mass, and that's how many grams that weighs. But again, use a conversion factor if you're not quite sure. And this is just the opposite. If it's let's do an easy one. Maybe, is there an easy one? Maybe this one. 60 grams of glucose. And it's 180 grams per mole. Well, do I have even a mole of that glucose? No, I have less than a mole. I have 1/3 of a mole, right? So what you do is you divide the mass by the molar mass, and that gives you how many moles you have. Same thing here. I have 248 grams of sodium oxide, but if it's 62 grams per mole, how many moles do I have? 4 moles. But again, feel free to use a conversion factor if you're a little bit afraid of it. I don't know if I'm going to bring up this vocabulary word, but just so if it comes across on the final, you know what it means. A solution that is holding as much dissolved solute as it can at that temperature is said to be saturated. So that means if it's saturated and we tried to dump in some more solute, it would just fall to the bottom and not dissolve. These are more molarity stuff, which we'll skip. I'm not going to cross it out. You do need to know this, but I'm not going to do more of those. We'll skip those. And then there's precipitate. So let me go back and explain how you figure out if a precipitate forms. And let's see if I can really quickly, I'll try to write this down. Magnesium chloride, silver nitrate. Okay. Magnesium chloride, silver nitrate. Magnesium chloride, silver nitrate. Okay. All right, got it. So here's what you do, which again, I'm not going to write that down. What you're doing is you're saying you're mixing these 2 solutions. So there are 2 aqueous solutions, dissolved ions, and now we're going to put them together and see if a pair of these are insoluble together, that they can't coexist together, and they'll form a precipitate, they'll form a solid. So in other words, we're trying to figure out if 2 of these are insoluble with each other. So what you do is you cross-check the cation of one with the anion of the other, and the cation of that one with the anion of that one. Okay, so let's do nitrate and magnesium. So we find nitrate. Is it insoluble with magnesium? No, everything's soluble with nitrate. So that pair will not form a precipitate. But what about silver and chlorine? Well, let's find chlorine, the negative ion, which is right here. Where's silver? Oh, right there. Chlorine and silver are insoluble with each other, meaning they will form a precipitate. So that's how you use this table, is given the 2 compounds, you check the positive ion of one with the negative ion of the other, and vice versa. And if either pair is insoluble with each other, that means they'll form a precipitate. As you can tell, my voice, it doesn't have much longer. I'll try to get through these last pages. So I'll let you practice some more of these. There's probably another one later. I'll try one more. But the other thing you have to do, especially when we start balancing equations, is to understand what the precipitate is. So going back to the example that we did, we said that silver is going to form a precipitate with the chloride. But is it going to be AgCl2? No. We just had 2 chloride ions with the magnesium. We got to make sure it's a formula that works. So what is the charge of Ag? +1, right? We know, we kind of memorize that, but if nitrate's -1, silver has to be +1. And what's the charge of chloride always? -1. So that formula has to be AgCl. Now another pair, maybe we'll try to do this for another practice. Let's go back to the solubility table. Iron 3 nitrate and potassium carbonate. Let me visualize that. Iron 3 nitrate, potassium carbonate. I think I got it. Okay. So what we do is, let's check iron. Well, we'll do one that's not going to form. We'll check nitrate and potassium. Well, you go up here, find nitrate. Okay, they don't form a precipitate. What about carbonate and iron? Well, find carbonate. It's right here. Where is it? Right there. So where is iron 3+? It's implied to be here, right? So those are insoluble. Now let me go ahead and answer that question we're about to answer. What is the formula of the precipitate between iron and carbonates? Well, I didn't get the formula right. There it is. If each nitrate's -1 and I have 3 nitrates, what's the charge of iron in that compound? 3+. And what is always the charge of carbonate? 2-. So what's going to be the formula of that precipitate? Fe2CO3. 3. That's how you do those. Okay. Hopefully that's enough of that type. I know how to do those problems. Yeah, my voice is almost gone. So that was that problem said. We're almost done because I think, again, more review. I think everything on this is a review of stuff I did in the previous problems. Yeah, even that one is kind of like, I'm not going to do that full thing, but if I wanted to do it really quickly, magnesium sulfate, if it's aqueous, means it is dissolved. So I have magnesium 2+ floating around and sulfate floating around. Lead nitrate's aqueous, or lead 3 nitrate. So that means I have a lead 3+ floating around, and I have 3 nitrates floating around. Sorry for my sloppiness. And now, so I think I said, I said assume it forms a precipitate? I must be, because I'm asking you all these questions. So if we use the solubility table, we'll see that a precipitate forms. And it's not going to be with the nitrate. So the precipitate's going to be between the lead and the sulfate. Well, what's the charge of lead? Oh, I said 3+, my bad, 2+. That's lead 2 nitrate. So let's go back. Sorry about that. Again, I'm trying to get this done. It's lead 2 nitrate. So I have a lead 2+ and 2 nitrates. You probably caught that and were panicking that I was doing something weird. So it's going to be between lead 2+ and sulfate 2-. Well, that's going to be a 1-to-1. So it forms a precipitate that falls to the bottom. So down here, we'll see our lead sulfates precipitating. Okay. The spectators are the ions that stayed dissolved in the solution that did not form a precipitate. So the magnesium stayed dissolved, and those nitrates stayed dissolved. They did not form a precipitate. They're still floating around. Only the lead 2 sulfate precipitated. So the spectators are the Mg2+ and the NO3-. I don't know if I'll ask that, but I might as well go over it. All right, let's see if there's anything else or if that's it. We'll do a couple more. This is getting right when we're about to do the new unit, so you'll see a lot that are just review questions or starting to bring up the new unit, which I'll get to tomorrow if my voice heals. So again, identifying the difference between ionic and molecular. Compounds formed between cations and anions are ionic compounds. Compounds formed when nonmetals share electrons, molecular. And I really haven't brought this up yet, but it's going to be in the new units. That again, if you have an ionic compound, it's held together by ionic bonds. If you have a molecular, it's held together by covalence. So BaCl2 is an ionic compound, so ionic bonds hold it together. NF3, nonmetals, that's molecular, that's covalent. Okay, anything else? Again, more of this, stuff about electrolytes and stuff. Which compound breaks apart into ions when dissolved? Well, duh, ionic compounds. And so we call an electrolyte something that when it dissolves, it produces ions that can conduct a current. And so remember that only soluble ionic compounds are electrolytes. So this last question on number 8 here, ethanol, is that ionic or molecular? That's a molecular compound. It's not made up of ions. So even though ethanol could dissolve or just on its own, there's no ions there, so it can't conduct a current. And so therefore it's not an electrolyte. And here, just make sure you remember your Brinkelhoff as the 7 elements that you should always write in the form of something 2 when they're by themselves. Anything else? 74, almost done. Again, a lot of reviews. Feel free to look over this. And maybe just to remember some of this, NaCl is soluble in water, which means it can dissolve. When you dissolve NaCl, it is the solute, the water is the solvent, and you form an aqueous solution. When you've dissolved as much NaCl as you can at that temperature, we say the solution is saturated in NaCl. If a compound could not dissolve, we say it's insoluble. All right, I'm just seeing if there's anything else here before we finish this. Yeah, this is when we start getting into the new unit. But again, plenty of practice. You go back. I don't see anything else circled. Okay, that's it, I think. Yeah, again, this is for the new units, so we'll get to that later. All right, so hope you found that useful. Sorry that was longer than I thought, but I hope that you do really well in the final. See you guys.